All right. So if you think about the first unit as kind of like us just getting a sense of the underlying structure of things, and now as we move forward, it's implementing those things. All right. So now that we know a little something about polar coordinates and parametrics and vectors, like what can we do with that? All right. What's the calculus of that stuff? All right. So I figured I'd go back to basics, sketch the point of 1, -2, 3 in three-dimensional space. I included this nice little diagram here. So 1, -2, 3, so that would be 1 unit in the x direction, in the positive x direction, -2 in the, or 2 units in the negative y direction, so that puts you here. And then really the only estimation is going to come into play with plotting 3 units in the z direction. So here's 3 units in the z direction. So you could use the index card approach, but if I give you this nice little grid, then you could kind of count boxes and things get a lot easier. So yeah, maybe I'm not counting boxes, but I'm counting the diagonals of those boxes. I have 3 of them, so I just go 1, 2, and I just need 1 more. All right? So it's a whole lot easier if you have a sense of scale. But personally, I don't like going that route. I don't like giving the scale, because I don't want to be limited to a graph that only goes from -5 to 5 or -10 to 10. You know, what if we need to go to like 3,000? You know, so we want to have the freedom to create our own scale. All right. So I'm going to draw a nice looking vector going to that point. All right, relatively nice looking. There's my arrow. And so you're talking about this being the base underneath it, and that's that point in space. But again, you're creating a 3-dimensional diagram on a 2-dimensional surface, like the surface as in the paper that you're writing on. So, you know, it's not going to look perfect, and sometimes you kind of have to suspend your disbelief, blur your vision a little bit, be like, yeah, I can kind of see it, but it's definitely there. You know, whenever I need to kind of get myself grounded, I try to find like a corner of a room. Of course, this room doesn't have like clear corners, but or like I guess in the back. That's as close as you're gonna get. I could do it with this, I guess. It's not gonna be perfect, but it'll kind of work. So you have x-axis, y-axis, z-axis coming up the wall. And so really, I mean, you're just counting boxes out from there. So when we say, well, I'll use 1, 2, 3 because it's, you know, I can't go in the negative direction because the wall is solid. But I go out 1 unit in the x direction, then 2 units in the y direction, and then 3 units in the z direction. So 1, 2, 3 puts me about right here. All right, so this is where that coordinate would be connected to the origin. All right, so to get that from a diagram, it really kind of takes a little like, I can see it when I tilt my head this way, but it's definitely not something that always comes naturally. All right. So what we want to do is write equations of planes passing through coordinates. All right. So the key is, well, the main ingredient, I guess, is what kind of plane? Are we talking about a horizontal plane, as in parallel to the xy axis? Are we talking about some kind of vertical plane, like as in parallel to the yz axis or the xz axis? Or are we talking about some kind of skewed plane, something on a slant? All right. So in this case, we're talking about parallel, so that's fine. But coming up with a visual of it can be helpful. I mean, because there's rules, you can follow the rules, but I think the visual is really what makes the big difference. So just kind of off on the side, I'm just going to draw like the roughest of rough sketches. Well, that's too rough. X, Y, Z. 3, 11. Yeah, so like over here is where 11 would be. So something like this, and then we're going up 7. So it would put the point somewhere around right here. Well, it's a point, it's not a vector, so it's just I'll just plot that point, 3, 11, 7. All right, it's saying it's going to be parallel to the YZ plane. All right, so that means what you're dealing with, I mean, if you're using the corner of the room analogy, then what we're dealing with is something, if I have 3 units in this direction, 11 units in that direction, but then 7 up, so I'm like right here, I need a plane that's going to be vertical, but also parallel to the wall with the door on it, right? So it's got to be that kind of orientation. So what we need to do is just figure out, okay, that's cool, but what kind of plane would that be? Well, if you think about it, certain things are going to remain constant, all right? So if I varied certain things, then it wouldn't really work out. But because I'm going to hold the y values and z values constant, hold constant, I'm sorry, I got that backwards. I circled the wrong thing. Hold the 3 constant. The y and z would be allowed to vary. Allow to vary. All right, and that's because the length horizontally and the height, that could be anything. But the one thing I need to stay fixed would be that value of x equals 3, right? In order for it to be parallel to the YZ axis, all right? Because it has to be equidistant at all points from that YZ axis. It always has to maintain an x value of 3, otherwise it all falls apart, all right? So that's my key, telling me that the x equals 3 plane is the only one that would satisfy this. And that's really the justification behind the third rule there. The plane that is parallel to the YZ plane and contains point A, B, C, blah, 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 it can be written as x equals A. Now, I do a lot of hand waving, and I remember when I was a student, yeah, hand waving was a thing. Doesn't mean that you have to like it. So we don't have to like it, because we have GeoGebra, which is, I think it was Digital Link, right? It's Digital Link. Unless they changed it. Oh no, there it is. All right, so I got my 3D calculator. I'm gonna kill this plane, I don't like it, it's just ugly. When you set up your GeoGebra on your own computer, I recommend, for the 3D one, under settings, for x-axis, label it as x, the y-axis, label it as y, and the z-axis, label it as z. Just so you can kind of get the right orientation. All right, so this is what my diagram is. And again, the coordinates are 3, 11, 7. So that's the point in space. It's kind of hard to, again, visualize. It's on a 2-dimensional surface, or at least it seems like it is. But if I rotate, I could see, if I have the y pointing, well, relatively straight out, you could see that the A is right on that 3 line. And so now if I plot x equals 3, oh, I don't want it as a name. I want it as a plane. X equals 3. All right, so it'll show me nothing until I turn it. All right, because it's a 3-dimensional graph on a 2-dimensional surface. So if you have it at the right angle there, it just looks like a line. I mean, it didn't show anything at first, but now it's looking like a line, but that's only because you're getting the side view of it, right? So you're standing out at positive infinity, looking at this plane along the y-axis. That's what you're gonna see, all right? But this is in fact what that plane would be. And you can zoom in and out and see. All right. Something like that. It becomes a little clearer, I think. All right, so you can get it at different angles and so on.
That's it.
Right there, I guess. Yeah, but just so you could actually see the plane, right? And what I can do, just to really verify it, I can plot the plane x equals 0. And you can see that they are parallel planes. All right? So one plane is parallel to the other. So the the YZ plane is also known as x equals 0. All right? The XZ plane is y equals 0. And the XY plane is z equals 0. Now that might seem like a bunch of facts that I'm throwing out at you, but oh, that's funny. So that might seem like a bunch of facts that I'm throwing out at you, but when I write this one, the XY plane, z equals 0, that should make perfect sense. Because the XY plane is what you've been talking about for years. X-axis, y-axis, all right? That contains no mentioning of z, all right? But in reality, if you're looking at it in the 3 dimensions, you're always working at the z value equal to 0. That's ground 0, that's the floor level, all right? And so everything from there is either going to be a positive or a negative movement in the z dimension, all right? So the XY plane, the ordinary XY axis that you've been working with for years ought to be z equals 0. So if that holds true, then all these others should as well. All right. So then, looking at number 2, it says find the equation of the plane passing through these points. All right. Now it just so happens that these points have a common -2. So the other values vary. So x and z are allowed to vary, but y is held constant at 2. So I'm actually going to write that, just for note-taking purposes, just so you get a sense of the rationale here. X and z are allowed to vary, y is held constant at -2. All right, so this is indirectly saying that you're looking at something that's parallel to the xz plane. I'll just write parallel to xz. All right, and so therefore you could just say y equals -2. However, I don't know that you need to write any of that in order to come up with y equals -2, because if you're just looking at the thing that is defined within this problem as something that's unchanged, or something that you could rely upon as a given relationship, it would be that y is always equal to -2. All right? If you plot all 3 of these points on the same set of coordinate axes, they'd be coplanar. All right, they'd all be on the same plane. And that plane would be parallel to the xz, right? So it would be a kind of vertical plane, but oriented so that it's parallel to the xz axis. You could also find the distance between points in 3 dimensions. That's a little bit more interesting, at least in terms of the structure of why it works the way it does. The formula is pretty straightforward. It's the distance formula from 2 dimensions. So here is distance in 2 dimensions. So all we're doing is throwing on a third dimension. All right, so that's not bad. But then you might wonder what's the justification for that, and it's a good question to ask. So I'm gonna take the time and prove it here, which maybe you don't want me to do, because if I prove it, then that means that you're on the hook for the knowledge. However, I will say that this one, in terms of a proof, I don't think this is something that you'll be afraid of. All right, I'll show you. You'll see. I think you'll believe me. All right, so maybe that's too thick. So I'm just going to focus on this right triangle. Now, again, it's another one of those suspend your disbelief kind of things, because you look at it and say, well, that doesn't look like a right triangle, but it's a perspective drawing, so it's supposed to be a right angle there, even though maybe it's a little bit off. But I have a distance y here and a distance x. Now the Pythagorean theorem tells us that x squared plus y squared would be equal to, we're calling that side c, so c squared. All right, so what I would get is c is equal to the square root of x squared plus y squared. All right, now, so I have the value of c. I could throw in a vertical side along with c, and that'll help me come up with the hypotenuse, which would be the distance that I'm looking for. All right, so I can now say c squared plus z, because that would be a vertical distance, z squared would be equal to d squared. All right, so I have that little radical there. I could plug that in, but I also happen to know that c squared is the same thing as x squared plus y squared, so I could just make that wholesale substitution there and come up with x squared plus y squared plus the z squared that's already there is equal to d squared. And then I could root. All right, so that gives you a general definition. However, it doesn't really get it in the precise form that we had earlier, or that's stated there. So what I could then say is let x equal the difference between some x value and some other x value. Same thing for y and z. Because in each case, in order to get those lengths in a coordinate plane, I'd have to have some y value here and some y value there. Subtract them, I get this length. Some x value here, some x value there. Subtract them, I get that length. Some z value here, some z value there. Subtract them, I get this length. All right, so these are the assumed relationships, and then from that, we arrive at our conclusion that the distance has to be equal to x2 minus x1, quantity squared, plus y2 minus y1, same deal, quantity squared, plus z2 minus z1, quantity squared. I mean, none of that does anything to answer the question that was posed, and that is, what's the distance between the 2 points? But, I mean, I think that's the bigger learning objective there, is to understand where the formulas come from. I don't know how many people are going to go the advanced calculus route, because you may not know what all the courses are, where it all ends, but after you finish all the quote-unquote introductory calculus, they have a whole slate of calculus courses called advanced calculus, and well, usually advanced calculus 1 and 2, but then after that it's organized by topic, so you might take ordinary differential equations here, but then you might take partial differential equations, which is kind of like the differential equations course that you would take after you take this course. Right? So a lot of different things come into play, but advanced calculus, it goes all the way back to the beginning, and you learn how to prove all the formulas or all the rules that you learned, all throughout the calculus process. So this stuff is like the norm in a class like that rather than the exception, right? But if it's the kind of thing that you're like, oh, this I don't mind this, then that might be for you. But based on all the eager looks and smiles on your faces, I can tell that maybe not. All right.
What career path requires these courses?
Pure math.
Really?
Yeah. Or someone like me who decides, I'm going to be a teacher, and also I want to take those courses too. So.
Have you taken them?
Yeah, it was interesting. So 0 minus -3, 5 minus 0, and then 0 minus 2. So what do we got, 38? Root 38? Barring anything catastrophic. That would be our distance. All right. Now, GeoGebra will do that for you, but, I tend to sing the praises of GeoGebra maybe a little too much, because it's like, yeah, GeoGebra will do that for you. It'll do a lot of things for you, but it won't do it for you on the test, so what's the point, when it comes to doing solving out problems for your own interests, like if you're applying this in a science class or something like that, then GeoGebra is a good resource, because maybe you just want the numbers crunched. Me personally, I sometimes use GeoGebra to see if you, on a test, came up with an equivalent correct answer. I did it one way, I got an answer. I know my answer's right, most of the time. But then sometimes you come up with a different answer, and I'm like, well, maybe there's two right answers. So I pop it in GeoGebra and take a quick look, and it's very quick and easy to verify. So with that in mind, you might use it as kind of like a mobile answer key, where you're like, all right, I got to do this by hand. I got to come up with the cross product or a vector sum or something like that. You try it by hand and you pop it in GeoGebra to see how it played out. All right. So we have 10.7.4. All right. So program. I'm going to run my distance in 3D formula or program. The first coordinate, it has three components. So we have 10, 7, 4. It'll ask for the second coordinate, -1, 3, -2. And it tells me what my distance is. All right, so that's pretty solid. All right, maybe you want not a decimal answer. Well, tough. You're getting a decimal answer. I don't know what else to tell you. No, it's fine. Just square it to see if it's the square root of some number. It happens to be. And so there you have it. All right. You could actually change the program if you want so that it doesn't give you the actual square root. It'll just give you the radicand. And so you know to just put the radical over it. But then, you run the risk of thinking that that's actually the distance. So you'd have to put a note in your program to say, the square root of this number is your distance. Or this is the squared distance. Something along those lines. But I look at it and say, well, if I know it's a square root, just square it, So I'm going to pop back to this. If anybody had trouble with the program, I can walk you through it later. But I'm also, like I said, I'm also going to save this and post it up on YouTube. With that being said, I guess I should save it.
How do you save your program?
Just by quitting out. It's automatically locked in.
And then you go back to it?
And then go back to it, hit program. Then it should be in your list, your execute list.
I've got a question. Gave me an error.
Gave you an error?
Yeah.
That's disgraceful. All right, I'll take a look in a second. Just write program. It's dist 3D. I'll save that, and hopefully it'll work.
That's where it's right.
I fixed it.
Did you?
Yeah.
All right. All right, well, clearly I walk away from the microphone too frequently. So, okay, well, I have a video, and I'm going to post that up on YouTube in a little bit. Actually, I'm posting it up right now. Yeah, it's just one of those things like, I mean, do you need a program to compute distance for you? No. I just kind of look at it like, while you don't need it to do that one thing, that skill is pretty useful, just because I think it's valuable. You know, you have a skill that you can apply in a number of different areas, and so why not, you know? So we have the center. We know that the distance from center to the point is the square root of 173. That happens also to be the definition of a radius. Distance from the center to the circumference of a circle or a sphere is known as the radius. So we have what we need, and so we're looking at x minus 10 squared plus y minus 7 squared plus z minus 4 squared is equal to the square root of 173 squared, which is 173. All right, so I'm going to pop a nice star on number 2 for you. Talk a little bit about vectors in space, and then we'll talk about the tech assignment, and then we'll do the quiz. All right, so in space, vectors are written with 3 components. All right, so that shouldn't be shocking, because when it was in 2 space, it had 2 components, because ordered pairs have 2 elements. All right, so now we have 3 elements to work with, so you'll have an ordered triple. All right, that ordered triple can be represented in IJK notation, but also comes along with a set of properties and all that good stuff. And the good news is, these are not really new properties. These are the same properties that they were in 2 space, just with a 3rd component. All right, so vector addition, vector subtraction, we're just adding not only the x with the x and the y with the y, but also the z with the z. Scalar multiplication, we're not just distributing the k to the x and y values, but also to the z values. All right, so it's as simple as that. You also have vector magnitude, but that's the same idea as distance formula. All right, so magnitude in 2 space was the distance formula with 2 dimensions. Now it's the distance formula with 3 dimensions. The unit vector, it's the same deal. All right, that unit vector is, you're taking the vector and dividing it by its magnitude. All right, whether you have 2 dimensions or 30 dimensions, it doesn't make a difference whatsoever. It's all the same. All right. So the last thing that we're going to cover in new material tonight is called a dot product. It's very, very easy. but there are a lot of nice little consequences that emerge from the concept of the dot product that really make it a powerful, powerful tool. All right, there's two types of multiplication when it comes to vectors. You have the dot product, and then you have the cross product. So tonight is dot product. Next class, we'll start off with cross product. All right. So when I'm dotting u with v, I'm taking the corresponding parts, so 3 and -1, and multiplying them. Then 5 and 3, and then 2 and 0. So corresponding parts get multiplied, and then you add the results. No, because the answer is going to be a scalar. Yeah, not a vector. Yeah. Yeah, it's going to give you the vector that is perpendicular to the first two vectors. So it will be an IJK. So we get a result of 12 here. All right. Maybe, I'm just thinking it's either, no, I don't think we have time for it tonight, but I will talk to you about what the hell this 12 means, because that's kind of important. But for now, we'll just work on the skill. All right. For number 2, it says find the scalar product. Scalar product and dot product are synonymous. They mean the same thing. So dot product. Say it again. Sine of u plus the sine of.
Or wait, plus is it like u multiplied by the sine of the angle?
That's part of it. That's another variation on the dot product formula, which we're going to get to. But if you're looking for the angle between two vectors, part of it has to do with the dot product. So that when you solve for the angle, you get it as a result of the dot product. But that's something else that we're going to get to in a little bit. All right. So 10 times -2 plus -4 times 1 plus 7 times 6. So whether it's in component form or IJK notation, it doesn't really make a difference. It's the same operation or a set of operations. If I can get my pen to work. So 18. All right, so computation-wise, it's not crazy. Now on your calculator, I think this falls squarely in the category of, yeah, it might be more trouble than it's worth, but I can show you really quickly just how you would handle a dot product in your calculator, and then you'll say, yeah, I'm not doing that. So you'd use squiggly brackets to input your vectors, 3, 5, 2, for example. And then another squiggly for -1, 3, 0. So what that'll do is that'll actually carry out the multiplication of the corresponding parts. And so at that point, it should be easy enough to just add them together with a little mental math. But you could also find the sum. So second stat, math 5 is sum of that previous answer. And it'll do it for you. All right. I kind of breezed through that, not because I expected you to necessarily remember every step after I show you in the previous of periods of time, but because I don't expect you to do that. these calculations are not hard. So why do you need a workaround? You know? That being said, can't tell you how many times on a test, and we got like 12, what do we got? 3, 5, 7, 9, 11. Yeah, 12 people in here. So, yeah, like 8. Nah, that's too high. 6 or 7 people, about half the class, at some point, is going to think that 2 times 0 is 2. It happens every friggin' semester. Every time I teach this course. And only with the dot product. Multiply everything else by 0, no problem whatsoever. But for some reason with the dot product, 2 times 0 becomes 2. I have no idea why. So maybe you do want to work around. You know, because sometimes you need a second set of eyes on it. Because it's like, no matter how many times you look at it, 2 times 0 is going to continue to become 2 until you do something about it, you know? So,
2 times 0 is 20.
or 2 times 0 is 20, exactly. What's 1 plus 1? 11. So the properties, commutative property of dot product and distributive property and things like that, they all seem very familiar, so I don't think you're going to have too much trouble with that, so I'm going to pop a nice little star there.